All right, in this video, we're going to talk about free fall. That's another form of motion. We can apply our kinematic equations to it because it is movement. And so let's get right into it. And there we go. Let's get right into it. Give me a minute here. I keep turning off the wrong thing there. Okay, so let's get right into it. So basically what free fall is anything, any movement that is only affected by gravity. And what kind of actions are that? Is something that is dropped or something that is thrown. So if it's dropped, no other forces acting on it, just gravity. If it's thrown, you've got gravity acting on it. So let's give a couple of simple examples here. You've got a cliff. You've got somebody standing on the cliff and he wants to watch as he drops a rock, and he watches the rock drop all the way down. It is only affected by gravity. Or you have somebody sitting here and he's got a ball and he decides to play catch with himself, so he throws the ball up and then the ball comes back down. So we're going to talk about each kinds of those examples. They're actually pretty simple. The tossing has some things to consider, but for the most part, these are really simple concepts to work on. All right, so let's talk about the cliff. Let's talk about just dropping the ball. And what we're going to do is we're going to talk about this in relationship to the equations. All right, so standing up here, precariously balanced on a cliff, and we drop a ball, and we always, unless stated otherwise, we always assume that we're dropping the ball exactly from the top of the cliff. Now, in reality, we're a foot and a half above that as we drop it. But maybe we're laying down right here and we just drop the ball off the cliff. I don't know, but that's what we always assume unless otherwise stated. All right, so once he drops this ball, the only force acting on it is gravity. And gravity, usually we represent acceleration. So we represent acceleration with A. All right, so A for short for acceleration. But because gravity itself is an acceleration, and it's a very important one, we give it its own designation. We give it a G. So instead of SUVAT, we now change this to SUVGT. SUVGT. You can keep the A in there if you want to. It's acceleration. We just represent it as G so that we know automatically that it's negative 9.81 meters per second squared. It's negative because it's downward. We are being pulled down to the earth with the force of gravity, so it has to be negative. All right, now sometimes we just work with the magnitude of the gravitational acceleration, in which case we don't worry about the sign. But for the most part, we are going to worry about the sign. It is going to be important for these equations. All right, so free fall is actually very much easier to do than other, let's say, horizontal motion problems, because you already know a couple of things. If you just drop this rock, you know your initial velocity is 0 meters per second because it started out at 0. There was nothing on. You're just holding it out there and you just let it go from your hand. So the initial velocity was 0. And in free fall, always, 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 the gravity, I should make it a G, equals negative 9.81 meters per second squared. Now I will say this. IB makes 9.8 meters per second squared the standard, and sometimes they estimate it to 10 meters per second squared. I don't see any problem with going a little bit more precise and adding the 1 here. It usually does not change the answer. It's usually close enough, but I figure why limit the number of significant figures? We can always change that at the end of the answer when we get it. But if you use 9.8, I'm not gonna be picky about that. That's totally fine. So we need 3 variables to solve for any of the other 2 variables in free fall, and we've already got 2 of them. So free fall just gives us 2 of them. Now, initial velocity may change. What if I threw this rock down the cliff? Then I've imparted an initial velocity to it, and in that case it would not equal 0. But for the most part, actually not for the most part, if you see the word drop, that means it's 0 meters per second. All right, you just dropped it, you didn't throw it. All right, so that's all there is to dropping something. And it doesn't even have to be on a cliff. You can just be standing there on the floor. Sorry, that's an inclined floor, I guess. And you drop it, and this all applies to this just as well, right? You're dropping a certain distance. You still have the pull of gravity is the only thing acting on it. Your initial velocity is 0 because you dropped it, and so okay. That's just keep that in mind. It is very simple. And of course, I will apply this to a few problems at the end of this. All right, so that's all there is to dropping for free fall. Now then there's another kind of free fall which isn't intuitively obvious at first. But what if you're standing here firmly on the floor and you throw a ball straight up? Well, that's not free fall, you threw it, right? That's not quite true. While this ball is in your hand, gaining the momentum, the velocity that it needs to fly straight up, while it's in your hand, yes, it is not under free fall. The second it leaves your hand, it is in free fall. The only force acting on it is gravity. And that means, in this case, the velocity is up, but the acceleration is down. So what's going to happen to this ball? The velocity is going to decrease, 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 decrease until it gets to the point at the very tip where just for that instant it's going 0 meters per second. Now that will become important here in just a little bit. And then what does it do? It comes back down. And because when it comes back down, its velocity is in the same direction as gravity, it speeds up, correct? And it speeds up, speeds up, speeds up, speeds up. And in fact, when it gets to exactly the same point where it left your hand, it's going exactly the same velocity that it left your hand, only in the opposite direction. So the magnitude of the velocity stays the same. So you pick any point on either of these flight paths that are at the same point, and it's going the same velocity, the same magnitude of velocity, just in the opposite direction. Okay, because if you work it out with the equations, you can see that. Because the same force of gravity is working on both of them, and that's the only thing affecting them. So that's very important to keep in mind, that as you throw this up and it comes back down, that the velocities are the same. I'm sorry, the magnitudes, I guess I should say the speeds, are the same at whatever point along that flight path that it takes. All right, so let's try to do something with this. Just illustrate that this is a little bit more complicated, but it all makes sense. And if you just work on this, it'll be something you can easily do, and maybe even have some fun doing it. Okay, so let's say we've got our SUVAT set up here. We are going to, in this case, have an initial velocity. So we are going to have one. We are going to have a final velocity, right? We know our acceleration. We may be given our distance that it rises. We may be given the time that it's in the air, or we may need to calculate that. Now, the first thing that you have to realize is that to make this work, you have to realize this is in two different segments. Because if you don't, and this makes sense when you think about this, because you're going in opposite directions, they cancel each other out, right? So the segment 1 final velocity equals the negative velocity of segment 2. And so if you treat this as if it's one trip, the initial velocity would be, I don't know, you left your hand at 10 meters per second. Your final velocity would be negative 10 meters per second. And if you apply this, say you wanted to find out how far it went in the 1 second that it was in the air, S equals U plus V over 2 times T. Well, this is 10 minus 10 is 0, so the distance it traveled is 0. This is actually correct. To be honest with you, the displacement was 0. It left your hand and came back to your hand at the same point, right? So your overall displacement is 0, but that's not very useful. We know that. We know that intuitively. It returned to exactly the same spot, so its displacement was 0. But what was the distance that it traveled? And we can't use these equations under this circumstance to figure that out. So if we break this up into two sections, though, we can figure this out. So let me give you an example. Okay, let's say it leaves your hand, leaves hand at 10 meters per second. Let's say, let's see. So we've got initial velocity of 10 meters per second. I'm trying to set this up. I'm just making this up as I go here. Our final velocity for segment 1 is going to be 0 meters per second, because it's at the very top right there where it ends up being 0 just for that instant, and that's what we want to know. Negative 9.81 meters per second squared. So we can figure out from this either how high the ball flew or how long it took to fly there. So let's figure out first how high it flew. So the equation I'm looking for uses UVGS, UVAS, UVAS, so V squared equals U squared plus 2AS. S is going to equal V squared minus U squared over 2A. And if you do enough of these problems, you will have these kinematic equations memorized, and even their derivations that you need to do to get to the actual variable that you're trying to solve. Okay, so S equals 100, because this is 0. This is minus 100. Yeah, 10 squared minus 10 squared is minus 100 over 2 times negative 9.81. And so the distance that it traveled up is divided by 2 divided by 9.81. Sorry, I'm working on my calculator here. Is going to be 5.1 meters. Okay, so it went up 5.1 meters. Well, guess what? It's going to fall 5.1 meters too. So its total distance is going to be, as it comes back down to meters, is going to be 10.2 meters. Now, a lot of times you'll get asked a question, how high did it go? And so all you need to know is figure this. You may get the question, how far did it travel the entire time it was in the air? In which case you'll need to do both. Okay, so just keep in mind that you just double, well, yeah, double. Everything that goes up is equal coming down in the opposite direction. Okay, and so since we were looking for this distance only, we don't worry about the sign. We just add up those two displacements. Okay, so the time that it took, how long was this ball actually in the air? Again, if we go with the total time here as one thing, we'll have a total time in the air of 0, because it will come back down, everything, excuse me, all the vectors will add up to 0, and so time will be 0. So what do we do about that? We do it just like we do everything else with something being thrown vertically in the air. We break it into two segments, the segment going up, the segment going down. And so the time, we can solve for this. And I'm going to do my practice of using something that I did not solve for. And that would be V equals U plus AT, because and in this case we make that a G. And I'm doing this because what if I made a mistake on the S? Okay, I didn't really need this in this case, but there will be times when you need to use the one that you calculated. But if you don't, do a different equation with it. All right, so time is going to equal to V minus U over G is going to be equal to 100, let's see what, 10, sorry. Final velocity, no, I'm sorry, 10 minus 100, there we go, divided by minus 9.81. In this case, just to speed this up, I'm going to estimate this to be 10, is going to be 110, get my units right here, 10 seconds. So it's in the air for a total of 10 seconds. Let's see if I got that right. I do not have that right, because that didn't even, in my mind, I'm sitting there going, 10 seconds is a long time for a ball to be in the air. And a lot of you are probably screaming at me. The initial velocity was not 100, it was 10. So 10 meters per second. So this will round up, it'll come out to almost exactly 1.0 meters per second anyway. So 1.0 meter per second. Golly, sorry guys. This is the way I do things, and it takes me a long time to get things done because I keep having these little mind lapses. And you may have these too, you may not, don't worry about them, they happen. That's why you write everything out, and you can make sure that you're getting everything right, because when I wrote this out and I saw 100, wait a minute, 100, 10 seconds doesn't seem right, and so I could go back and figure out what I did wrong and got the right answer. So I'm going to apologize that when I do this it may confuse you. I've been teaching physics for 10 years, doing the same problems over and over again, and believe it or not, I still make these silly mistakes all the time. It has nothing to do with understanding, and I'm relating this to you. Making these silly mistakes has nothing to do with your understanding, all right? It just has to do with making silly mistakes. So that's what I call them. That's what I've called them ever since I was in school. That's whenever I missed a problem in math or in physics, it was because of that. It was because of making silly little mistakes. But there we go. All right, so we figured out time is 1 second, but guess what? That is 1 second to just go up, right? It took 1 second to go that 5.1 meters to go up, and now it'll take 1 second for it to come down. So the total time, if we need to figure out the total time it was in the air, is going to be 2 seconds, right? All right, so the main thing to understand with doing free fall, throwing things up in the air, straight up in the air, is that you have to break it up into 2 segments, segment going up, segment going down. There is a third problem, but we're going to spend another video itself on this, and that is throwing a ball horizontally, like a baseball, football, kicking a soccer ball. It has a free fall component to it, anything that flies through the air. But that is a little more complicated. It's called two-dimensional motion, and that's what we will cover next time. Okay, so let me come here and show you a few problems and how to work these problems. All right, a construction worker, and you don't even have to read this first. Write down your SUVAT. And I always do G when I'm in free fall, so that I, number one, understand I'm in free fall, and number two, that I know that this is automatically 9.81 meters per second squared. I don't even have to read anything if I know it's a free fall problem to have this much done. A construction worker accidentally drops, there's the key word, a brick from a high scaffold. What is the velocity of the brick after 4 seconds? We don't know its final velocity, and we don't know how far does the brick fall. We don't know how far the brick falls. Its initial velocity is 0, and the time is 4 seconds. I don't know if it hits the ground at that point or not. If not, well, this is one tall building for that brick to fall that long. But there we go. So let's go. It wants to know first, what is the velocity of the brick? It wants to know the final velocity of the brick. And we can use V equals U plus AT. And we can just plug in here. U is 0. So velocity equals negative 9.81 times 4. So the velocity is 39.2. We'll just say 39. We'll go with 2 significant figures here because that's all we've got up here in the problem. Meters per second. So 39 meters per second is its final velocity, which is pretty fast. And so it wants to know how far the brick fell. And so I can use S equals, and this is really nice, we don't even have to adjust our equations here, times time. So S equals, U is 0, and here I am using my final velocity, but I happen to know it's right. 39 divided by 2 times 4. So S equals 39 divided by 2 times 4 comes out to be 78 meters. Almost 3/4 the distance of a football field. That is a tall building right there. All right, so that's how you do it. It's very simple. You see, I did this very quickly. I would have done this a lot faster if I wasn't talking. These are pretty straightforward problems. Pretty nice. Okay. So let's try this one. A tennis ball is thrown straight up with an initial speed. Suvat. Okay, it's thrown straight up with an initial speed of 22.5 meters per second. Now, you see they're using the M over S. And I just pulled this problem off the internet. So I did not change that, but this is pretty common to see, but IB wants you to use this, and I actually prefer this. All right, it's caught at the same distance above the ground, so it leaves his hand, comes back to his hand. How far does the ball rise? Let's give here what we've got, 9.81 meters per second squared. So initially it wants to know how high does the ball rise. So this is only during segment 1, right? The segment where it's going up. How far does it go? And it wants to know how long does the ball remain in the air. So the total time of the trip. So we're going to have to worry about the entire time. Now we know its final velocity is 0 meters per second, even though they don't say it in there, because at the top where S equals, at that instant, it's going to be 0. All right, so again, let's see how high it goes. We have to use SUVA. I'm looking at my, and again, it's going to be V squared equals U squared plus 2AS. V squared is 0, so we can just solve this for, let's see, S equals negative U squared over 2A. All right, so that is going to be negative 22.5 squared. Now this is still negative. We are not, this is not like this. This is like this, okay? It is negative times 2 times 9.81. And this is negative. And so we're going to have negative over negative, which gives us positive, which is good because we threw the ball up. So it's going in the positive direction, so the answer should be positive. Let me work this out on my calculator. 22.5 squared divided by 2 divided by 9.81, and I get 25.8, and I'm going to go with all three here. 25.8 meters is how high that ball went. Now for the total trip, we've got to do both our segments, right? The trip up and the trip down. So all we need to do is figure out the trip up and then double that, right? Because it's going to be exactly the same coming down. So let's go figure out what our time is. T, we can use V equals U plus AT. V is 0, right? Final velocity is 0 because it's the very top. So time is equal to negative U divided by G. Okay. So put that in. Negative 22.5 divided by negative 9.81. Again, positive, because time can only be positive. So time's not a vector. It cannot be negative. We do not go back in time ever. It should always be positive. 22.5 divided by 9.81 is going to give us 2.3 seconds. So this is just for segment 1, right? Segment 1. We want the total time. So that is T1 plus T2, each of the segments, which is 2.3 times 2. So the total time that it was in the air was 4.6 seconds. Okay. These are very simple if you just keep in mind that you're talking about two different segments of motion when you throw a ball straight up in the air. All right, let's do one more because this one is, it's easy, but it's, you got to think about this just a little bit. All right, and drawing a picture is good. If you can, always draw a picture, especially in something like this. You stand on top of a 60-meter cliff, so S equals 60 meters. You throw a rock off the edge straight down. You did not drop it, okay? You threw it straight down. So obviously don't try this in real life. You throw down, you probably follow the rock down, right? With a velocity of 20 meters per second. So we have an initial velocity of 20 meters per second. Acceleration negative 9.81 meters per second squared. With a velocity, and on our S distance is 60 meters. Okay, so how long does it take to reach the ground? We don't know that. And what's its final velocity when it reaches the ground? All right, so to find these, let's see, let's do the final velocity first, just because that's going to be easiest from what I can figure out. So I need something with SU, let's see, I need SUVG, SUVA in the equations. So that is going to be the V squared equals U squared plus 2AS. V equals the square root of U squared plus 2AS. And I should make this a G. All right, so V equals the square root of 20 squared, which is 400, plus 2 times 9.81 times 60. Now both 60, I should say this, 60 is negative, right? 60 because it's down. Because it's down, 60 is negative. So this is negative 9.81 times negative 60, which is going to equal a positive, right? So V equals square root of 400 plus, work this out on my calculator, 2 times 9.81 times 60 plus 400. Take the square root of that, and I get of all that. I'm sorry, I didn't write that out, but took the square root of all of that, and I get 39.7 meters per second. All right. Now then, we could use, to find the time, we could use S equals UT plus 1/2 AT squared, and you can use your mighty Algebra 2 skills to figure out how to solve for T. But since we have the V here, and I'm sure you want to save time and get things done fast, unless you want to actually work with this one, we can go with V equals U plus AT and solve for T. V minus U over A is going to equal, V is 39.7 minus 20 meters per second over negative 9.81 meters per second. All right, so that is going to be 39.7 minus 20. Now, if you see this on a multiple choice test, let me just say this right now, multiple choice tests, you're not allowed to have a calculator. So if you see a problem that works out like this, you do it in your head. That's when it's okay to make this 10 meters per second and work that out. I'm going to get 9.7. And it's going to work out. This should have been negative. Somewhere up here, somehow this should have become negative, and I'm not quite sure where it didn't work out. So we should have, let me think here. It should be work it out. So I'm confusing myself here, which happens a lot. So 39.7, it's going negative 39.7. It was going an initial 20. And I'm trying to think here. This should have been, initial velocity is negative because it's going down. So that would be negative 400. And because that's negative 400, it makes a difference. I got the whole wrong answer here. And if you were writing along with this, my apologies. Nothing I hated worse when I was a student than having a teacher erase everything I just wrote down. But you know, it happens. All right, so I'm gonna actually work this out. So this is negative 400 because let's see, is this right? Let me think about this. This is negative u squared, so that is plus, so that is plus, so that is plus. This is negative, this is negative. We can't really use a negative square root, right? Or can we? So since we're doing a square root, the velocity, okay, plus or minus, right? Plus or minus 39.7. And this is where we just have to know that we're going down, so that velocity is negative 39.7. You have to do that. You have to be aware of your circumstances and realize that anything going down is going to be negative. The acceleration may be in the opposite direction, going up, so your rocket and you're accelerating up, or whatever. But in this case, velocity is negative 39.7 because it's going down. All right, so using our solve for time equals v minus u over a, or over g. So that equals negative 39.7 minus a negative 20 meters per second. I don't need the units. And I get over negative 9.81. Okay, I'm starting to like the looks of this better now. This is why, again, why I write things down, because I mess things up all the time, and I just do. I don't know if it's some kind of dyslexia thing or not, with dysgraphia, not dysgraphia, with numbers. I don't know. It's just kind of weird how that happens to me. So this is going to be negative 19.7 divided by negative 9.81. I feel so much better. And it's going to be, I think, a fairly realistic time too. So I mean, by that I mean it makes sense that it will have fallen this. So 19.7 divided by 9.81 is going to be 2.0 seconds. And that does sound about right. Okay. All right. So sorry about all of that confusion in getting this worked out, but hopefully if you watch carefully, and listen to my reasoning as I try to solve what I did wrong and how it went wrong, that you will understand how to work with vectors and things better, and what things to keep in mind. In this case, things going down, so everything had to be negative. Time cannot be negative, so we had to end up with a positive number, which we did. Okay. All right, so fortunately that ends that. You now know everything that you need to know. Work on the worksheet, read the pages that I give you in the Google Classroom assignment, and we'll work on this further in class. And next time we'll be doing the mother of all motion problems, two-dimensional motion. I'll talk to you then.